So this course, okay, first name is Engineering Mathematics 1. So only we call this is EM1. Okay, so this sem take EM1. Next sem you will take differential equation for maths. Okay, differential equation. And sem 3 you will have EM2. Okay, EM2. And fourth sem you have engineering statistics. Okay, so 4 mathematics subjects, and this is the first one and the easiest one. Okay, from past history, this one, normally student manage to get A minus, mostly, okay, mostly. It's all actually depends on your basic. If your basic is good enough, normally A is not a problem. If your basic is not up to the very good standard, normally B plus, B. Actually, not much student get B minus. Normally, they get a very good grade because this course is simple and some of the topics, actually, there are more to revision. We have already learned some of the topics like matrices, differentiation, integration. Okay, but we have some new subtopics. Okay, for example, differentiation and integration, we have numerical differentiation, numerical integration, which are new to you. So for this course, we have 3 learning outcomes. Okay, so upon completion of this subject, you should be able to describe, describe the fundamental concepts of, see, all these are the subtopics. Matrices, eigenvalues, eigenvector. Eigenvalues and eigenvectors may be new to you. That is an application from matrices. Okay. And complex numbers. Okay, I think most of you know what is the complex numbers. Okay. And interpolation. I think interpolation is new. Interpolation, we have differentiation, integration, and also the numerical differentiation and numerical integration. The last topic is the vector value functions. Okay, so LO number 2 is, you are able to solve mathematical problems that involves all these subtopics by using an appropriate technique. Because you will learn a number of techniques, okay, and different techniques are being used to solve different problems. Okay, so you have to know under this problem, this kind of problem should be solved by this method A. Okay, this one maybe method B. Okay, it depends on the nature of the problem. Okay, then the last LO, normally this apply in the assignment. Okay, normally assignment questions are mapped to this learning outcome. So that means you are able to apply the knowledge from engineering mathematics to deal with the engineering problems. Okay. And now we look at the breakdown of the course assessment. Okay, so you will have one test, okay, only one midterm test that carries 20%. Okay, 20% for one midterm is considered quite heavy. Okay, if you want to score well for this subject, you must score well for the midterm test because it carries 20%. Okay, apply heavy weightage at this midterm. Okay, and you have 3 quizzes. Okay, 3 quizzes that carries 10 marks. And 1 assignment. Okay, this assignment normally is a group assignment. Okay, group assignment. Normally 4 or 5 students in a group. Okay, 4 or 5, I'm not sure for this semester. I will let you know by the time. And you want to form your group or I form for you? I give you a choice now. You want to form your own group for the group assignment or I form randomly for you? You want your own group? Okay. So by the time I'll let you form your own group if you learn. Okay. And last one, final exam. Okay, final exam, 60 marks. Okay. Okay. You know what is you're from diploma of poly matrix STPM, right? So you know what is the past year final exam question paper, past year, right? So you can try the past year question to face this final exam. Okay. And I will also give the tutorial questions in the ULearn. In this one, if you enroll into this ULearn, okay, for every single week, Okay, I will show what is the learning outcome, for example, this week. By the end of this week, you should be able to apply the basic operations of a matrix, compute the determinant of a matrix, and also compute inverse matrix. This is the learning outcome of this week. Okay, so you can get the slides of the lecture from here, and also the tutorial. Okay, tutorial questions for every single week. I have uploaded the lecture notes and also the tutorial questions. Okay, tutorial questions. I won't check your tutorial questions. I won't ask you to submit your tutorial questions. It's all on you, whether you want to try or not. Okay, if you want to score well, okay, try the tutorial questions. Okay, try. And if you have any questions regarding to the tutorial questions, you can ask during the class time. Okay, I will discuss the questions. Okay, if you have any questions, problems on the tutorial questions. Okay, but I will check your tutorial questions. Because your tutorial questions, for example, this one. Okay, I give the question. Okay, for example, number one, given the matrices. Okay, evaluate blah blah blah. Then answers. Final answers are given. Okay, final answers are given. So you can check what you want. You can discuss with your friends. And if you found that your answers are different from the one that I give here, you can let me know so that I can double check. Okay. So I want you to learn independently, okay, on this tutorial. Okay, so up to week 14, I have uploaded the slides and also the tutorial questions. And actually the slides are taken from this website. Okay, this is the website of U10, OCW U10, OpenCourseWare. Okay, OpenCourseWare. This is the website for certain subjects. Okay, for certain subjects. That's what you can see here. Okay, these are the subjects that the lecturer have developed the slides and published under this OCW U10. Okay, so for mathematics subjects, okay, engineering maths 1, okay, part 1, part 2. Okay, part 1 means the slides from week 1 to week 7. Part 2 is week 8 up to week 14. Okay, so you have this engineering maths 1. You have the differential equations for SEM 2. And you have the EM2, this two, EM2 for SEM 3. Okay, and for the SEM 4, the one I'm not sure whether it's still in the progress or what. Okay. Okay. Any questions? I will use the slides. Okay, I will use the slides from this. Okay. Actually, I am one of the lecturers who joined this one, okay, to develop the slides. So I will use the slides, okay, throughout this course. Okay. Okay. Next, we look at the syllabus. Okay, matrices. Chapter 1 is matrices, and this is also one you can learn before you are here. Okay, basic operations. That's mean the addition, the subtraction, the multiplication of the matrices. Okay, this one, multiplication, and then determinants and inverse matrix. I think this one you learned before. Okay, you have learned before inverse matrix that use the adjoint and co-equal matrices, right? Have you learned inverse matrix? So which method you use? Adjoint or Gauss elimination? Gauss. Okay, so here, okay, in this syllabus, okay, you will learn this adjoint. I think some of you maybe learned this before. Okay, so this is what you are going to learn in this week. Okay, week 2. Okay, week 2 is still matrices. Okay, matrices, but this is a numerical. Okay, numerical methods. Okay, if you look at the remarks here, This one, modern engineering mathematics. Okay, this is the reference, okay, for this one. Okay, you see modern engineering mathematics. That means this is analytical math. Okay. There are two approaches. Okay, this is one. One is analytical method, another one is numerical method. Okay, analytical method is a method that gives you the exact solution, the actual solution. Okay. And the numerical methods is the one that gives you the approximation, just an approximation with some errors. Okay. So normally what you obtain from the numerical methods is just in point forms. Okay. In not in a function form. Okay. From analytical, you get a function as the answer, but for numerical, you will get points. Okay. Normally we use four decimal places, the standard one. Okay. Okay, so this is under numerical methods. And for chapter 2, nonlinear equations. Okay, nonlinear equations, we will solve this by using 3 methods. Okay, these 3 methods. This is also under numerical methods. Okay, this is the application from the matrices, eigenvalues, and eigenvectors. So you will learn these 2 methods to obtain the eigenvalues and eigenvectors. So this polynomial method, okay, polynomial method is analytical method, and power method is the numerical methods. So you will learn 2 approaches to find for the eigenvalues and eigenvectors. Okay, normally numerical methods, it requires massive calculation where you need a calculator. So remember, you have to bring a calculator whenever you come to my class. Okay, here's when we are look into the numerical methods. Okay, you need a calculator. Okay, chapter 4. Chapter 4 is on complex numbers. Okay, and we have 2 weeks time for these complex numbers. For this one, I have to tell you beforehand. Okay, this subject EM1 is not only taken by the students from FTKE. There are also students from FTKM, FTKK, FTKIP. Okay, but among all these engineering faculties, only FTKE students need these complex numbers for the engineering subjects. Okay, so after the discussion among the lecturers involved, okay, we have agreed that this chapter is not covered under any assessment of this course. Meaning that you don't have this complex number for quizzes, for assignment, for final exam, for midterms. You won't see this question. But still, I have to introduce the complex numbers to you because this is very important. Okay, this is very important for the subjects of signals. I can't remember which subjects, but the one under Dr. Fami. Very important. Okay. So you still have to know what is the complex number, how to get the argument, the angle, the modulus, okay, how to change the form of the complex number from one coordinate to another coordinate. Okay, that's very important. Okay. Okay, next one, interpolation. I think this is new to all of you. Okay, interpolation. It is more like a curve fitting. Okay, given a few sets of points, okay, given a few points, we have to find out a curve that best fit to that few points. That is called interpolation. Okay, this is more used in research. Okay, and differentiation. Okay, differentiation. I think for this part, okay, this is just a revision for you because you have already learned the differentiation of exponential function, non-function, polynomial function, trigonometric function, right? So this is just kind of the revision to you. Okay, what's new to you is this one. Okay, this one is the numerical differentiation. Okay, this is under numerical. So this is numerical differentiation that involves this forward, backward, central differencing of first and also the second derivatives. Okay. We will just find up to second derivatives. Okay, same goes to the integration. You have one analytical part another part for the numerical integration. So for integration part, okay, this one I think, have you learned the integration by substitution? Yes, okay. So kind of revision and integration by parts. Okay, for integration by parts, okay, you will introduce a new, not new, a different types of method that can be used to solve the integration by parts problem. Okay, it will be much convenience, okay, much convenience where you will use it massively in next semester. So this one you will introduce a new one. Okay. Okay, numerical integration. Okay, numerical integration is used when you have an integral that you can't integrate by any of the techniques of integration. Okay, then we have to use the numerical integration. Okay, you see this by the time. Okay, the last chapter is vector valued functions. Okay, vector valued functions. Okay, this is more to the engineering topics. Okay, we use this in engineering topics. Okay, so these are the syllabus. Okay, any questions? Can I know how many of you from matrix? Matrix? One. There's only one. STPM? Poly, diploma? Okay. Any student other than these 4 entries? Is it diploma? Oh, foundation. Oh, okay. Foundation as well. Oh, okay. Okay. Okay, since we have learning outcomes for week 1, means that we have to start our class today. Okay. Okay, this is more to revision. Okay, matrices. Maybe some of the subtopics is new to you. Okay, so this is the lesson outcome. Okay. Today we will look at the first learning outcome, the basic operations of a matrix. Okay, and the determinant and inverse matrix, we will look at this on Thursday. Okay, now you know what is a matrix, but why we need matrices? Okay, why we need matrices? Okay, in general, matrices are used as a notation that represents simplified form of a linear system problem. So what is a linear system problem? Do you know what is a linear equation? Linear equation. When you have a number of linear equations, it forms a linear system. Okay, just like x plus y plus z equals to 1, and then 2x plus y minus z equals to 2. So all these are linear equations because x power of 1, y power of 1, z power of 1. They are all linear equations. But when you have 3 linear equations with 3 variables, the x, y, z, you have a linear system. Okay, so from a linear system, we can extract the matrix. Okay, we can extract the matrix from the coefficients of x, y, z. Okay, so that is a matrix. Okay, so normally, okay, with the matrices are used as a notation. Okay, a notation that represents a linear system. Okay, so that's means when we want to solve a linear system, we need a matrix. Okay, that extracted from the linear system. Okay, this is a matrix. Okay, a matrix in general form. Okay, so all these A11, A12, A13, they are called as entries. Entries. Okay, so the order of a matrix, okay, M is the number of rows. Okay, number of rows. n is the number of columns. Okay, so the order of a matrix is we call as m by n. Okay, m by n. Okay, for example, this one, 3 rows, 3 columns. This is a 3 by 3 matrix. Okay, 3 by 3 matrix. Okay, now when m equals to n, okay, when m equals to n, that means this is a square matrix. Okay, square matrix with order of n. Okay, so if the n is 1, if n is 1, meaning that you have only one column. One column, it will be something like this. So this is called as column vector. Okay, column vector. If m is 1, meaning that there is only one row. One row, this is called as row vector. Okay, something like this. Okay, row vector. Okay, so there are a few types of matrices. The first one is symmetric. Okay, symmetric. I think all of you know what is a symmetric matrix. Okay, and it looks like a matrix that is symmetric. Okay, symmetric along the diagonal. Okay, this is called diagonal. Okay, this is called diagonal. Okay, diagonal entries. Okay, so you see this one will be same as this. This is the same as this, and this one same as this. Okay, so this is a symmetric matrix if A transpose equals to A. Do you know what is A transpose? Transpose. Transpose means row change into columns. Row into columns. So you see this one, 1, -3, 5. This 1, -3, 5 is same as this 1, -3, 5. Okay, and the second row, you see this second row is -3, 2, 7. It's the same as this -3, 2, 7. And the last row, 5, 7, 0 is the same as this 5, 7, 0. Okay, this is a symmetric matrix, and transpose means we change the row into columns. Change the rows into columns. Okay, rows into columns. That is transpose. Okay. Or in another words, Aij equals to Aji. Okay, symmetric matrix. Okay, and there is another term called anti-symmetric. Okay, anti-symmetric matrix. Okay, this one, A transpose equals to -A. So this is similar to the symmetric matrix, but the difference is you have a minus here. Okay, you have a minus here. So what this means, okay, the value, okay, the magnitude is the same, but one of them is negative. 6, -6. 7, -7. One of them will be negative. Okay. So this is anti-symmetric. Okay. So this one, if you look at this, the anti-symmetric must satisfy this one. So this one means Aij equals to -Aji. For example, okay, for example, this entry is A12. This is A21. Okay, so A12 equals to -A21. It fits. Okay, it will satisfy this one. Okay, and for the diagonal entries, it must be 0. Why? Because it has to satisfy this. Okay, so we see this is A11. Okay, this one is A11. So A1, I is 1, J is 1. So A11 equals to -A11. A11 equals to -A11. So what is the values of A11? It must be 0. Okay, it must be 0. So that's why all the diagonal entries are 0. Okay, because it has to satisfy this equation. Okay, but for symmetry, okay, symmetric matrix, it has no issue with the diagonal entries. Okay, because this is the relation for symmetric matrix. Okay, Aij equals to Aji. So this one, A11. A11 equals to A11. A22 equals to A22. So any values will be, okay, it can be any values. Okay, but for the anti-symmetric matrix, the main diagonal must be 0. Okay, next one, diagonal. Okay, diagonal matrix. Diagonal matrix is a matrix where all the entries other than diagonal must be 0. Okay, all the entries here other than the diagonal must be all 0. Okay, so this is a diagonal matrix. But of course, this three, okay, this three actually at least one of them is non-zero, then it will be diagonal matrix. Okay, for example, this one. This is also a diagonal matrix, even though this is 0. Okay, and let's say if this is 0, okay, you have only 2 non-zero here. The rest are 0. Still, this one we can include this under diagonal matrix. Okay, but what's happened if 2 is also 0, 0, 0, 0? We don't call this as diagonal matrix. This is a 0 matrix. 0 matrix. If all entries are zeros, that is a 0 matrix. Okay. Okay, identity matrix. I think all of you know what is identity matrix. Identity matrix is a diagonal matrix where the diagonal entries are all 1. Okay, diagonal, it must be a diagonal matrix, but all the diagonal entries must be 1. Okay, so this is identity matrix. Okay, so far, any questions? Okay, next one, we look at the equality. Equality. If we say that matrix A equals to matrix B, then all the entries of A must be same exactly as the entries in B, right? Equality. Okay, addition and subtraction. I think you know what is this? Matrix plus matrix, matrix minus matrix. So for this to be valid, okay, or defined, for this A plus B or A minus B to be defined, okay, defined means valid, okay. It will happen only when A and B are from the same order. These two must be from the same order, then only you can proceed to get the answer. You can never sum up a matrix of this with a matrix of this because they are not from the same order. We will use the entries from the same location, we sum up them, we get a new entry. Okay, so this will only valid, okay, addition and subtraction will valid only when A and B are the same order. Okay. Okay, multiplication by a scalar. This is not multiplication between matrices. This is multiplication by a scalar. Okay, meaning that we have a scalar multiplying to a matrix. Okay, a scalar multiplying to a matrix. So meaning that all of the entries will be multiplied by -2. Okay, every single entries will be multiplied by -2. Then you get a new matrix. Okay, this is multiplication by a scalar. Okay, now we look at the properties of the transpose matrix. Okay, transpose matrix. A transpose matrix, when we transpose it once again, we will get back the original matrix A, right? A matrix A, we transpose, then we transpose again. We will get back the original matrix. Okay, this is the first property. Okay, the second property is when you have this A plus B and then transpose, okay, we can write in this way. Okay, they are equal. So A transpose plus B transpose. Okay, so this one means A plus B. You can sum up A plus B, and then you carry out the transpose. It will be same as you transpose the A, transpose the B, and you sum up that two matrices. Okay. Okay, for example, this one. A transpose plus A. Okay, and then you have a bracket, transpose. So this one, we can apply this property. Okay, we have the first matrix plus the second matrix, and then we have transpose. This is your first matrix. okay, plus this is your second matrix. So when we apply this, we will get the first matrix transpose plus the second matrix transpose. Okay, you get this. Then this A transpose, when you transpose once again, you get back A. Okay, so what this means when you see this A transpose plus A and then transpose overall equals to A plus A transpose. The conclusion is these two, okay, this A transpose plus A must be symmetric matrix. Why we say that this is a symmetric matrix? A transpose plus A is the same as A plus A transpose, right? This is the same matrix. The one in the bracket is the same as this. So that matrix transpose equals to the same matrix itself. That means it is a symmetric matrix. You still remember the one, symmetric matrix. A is symmetric if A transpose equals to A. So that's why, okay, this A transpose plus A, okay, this you just assume this as one matrix. Okay, one matrix. This matrix is the same as this. Okay, so B, let's say this is B. B transpose equals to B. That means B is symmetric. Okay, that means we conclude the B, which is the A transpose plus A, is a symmetric matrix based on the properties of the transpose matrix. Okay, this is one of the example. Okay, any questions? Okay. If you have any questions regarding to the topics that we discussed in the class, just hands up. Yep. Which one? You mean this one? You mean this one?
Yeah.
If you didn't show this, you can't conclude that this is a symmetric matrix, right? We can't get to tell, okay, by looking at this one. We can't get to tell what is the matrix of A transpose plus B. After we apply this step by step, and we get this one equals to this. And we know that this is actually same as this. Then from there, we make it. That's why we need to show this steps. Okay, any more questions? Yeah. Okay, next one, basic rules of addition. Okay, the matrix addition, okay, it satisfies these three laws: commutative, associative, and distributive laws. Okay, so for addition, matrix addition, okay, A, B, C have the same order. Okay, let's say A, B, C have the same order. So A plus B must be equals to B plus A. Okay, because this is the addition of the matrices. They're the same. So when we swap the order and it's still the same, that means it satisfies the commutative law. Okay, when we swap the order. Okay, this is commutative law. Okay, associative law means if you have three matrices, okay, now let's say we solve the first two. We solve the first two, then only we plus to C. And on the other hand, we solve the last two, then only we plus to A. Actually, you will get the same answer. Okay, so it means it satisfies this associative law. Okay, and the last one, distributive law, means we will R is a constant. R is a constant. So when R is multiplied to the sum of these two matrices, it means that R will be multiplied to A and also B. Okay, this is distributive law. Okay, so the matrices addition, it satisfies these three laws. Yep. Yes. Power of matrix, that is matrix multiplication, that is later one. Okay. Now let's try this exercise. Okay, try this. A transpose plus 2B. The final answers are given here. Okay, you can do a self check on your own. So if a justification finding, it is a good point. Yeah, you can see. Yeah, if one line sentence, just go back to if y and then this is like it might be minus minus is something. Okay, to get the transpose matrix, this one, okay, to get the transpose matrix, first row, okay, this row 2, -1, 3, you change into the column 2, -1, 3, and the second row you change into second column, and the last row into last column. Okay, So -2, 8, 1. So this is the transpose matrix. Okay, A transpose is not always equals to A. Okay, it will all A transpose equals to A if A is symmetric, but not all matrices are symmetric, right? So to get the transpose matrix, just change the row 1 into column 1, row 2 into column 2, row 3 into column 3. That is the transpose matrix. Okay, then you multiply 2 into all the entries, 2, 0, 10, -4, 8, 12, 6, 14, and -4. Then you sum them up. Okay, you sum them up, then you should get this. Number 2. Number 2. If you have start number 2, you can find that B has an order of 3 by 3. C has an order of 2 by 3. 3 by 3, 2 by 3, they are not from the same order. That's why we can't get to proceed to get the answer. So the answer is 19.9. Okay, 19.9. Okay, have you done question number 1? To B minus 5C. Okay, so this one, B has an order of 3 by 3. C has an order of 2 by 3. Okay, so we give a sentence since B and C have different order, and B minus 5C is fine. I get to solve this because there are from the different orders. Number 3. Okay, number 3. Okay, you can solve the D transpose first before you multiply to the 6. Okay, done. Okay, row into columns. Okay, row into columns. Okay, then you get this. After you stop, you get this. Every time before you start to compute, you should check their orders. Okay, if you found that the orders not valid for you to proceed, then just give an answer. But for number three is valid because B transpose. B after transpose, the order will be same as C. Okay, done. Any questions before we move on? Okay, next, we will look at matrix multiplication. Okay. So for matrix multiplication, before we multiply two matrices, we have to check their orders. Okay, we have to make sure their orders are valid for us to proceed. Okay, what it means valid? Okay, for example, let's say now we want to find for AB, A times B. So the matrix A has an order of P by Q. and matrix B have an order of Q by R. Okay, so the first matrix, the later value must be same as the second matrix, the first value. Okay, for example, here A has an order of 2 by 3. B has an order of 3 by 5. So you have to make sure this later value and the first value, they are the same. Okay, if they are not the same, that means undefined. Okay, so now they are the same. So the output of A times B, let's say C is A times B. So the output matrix C has an order of 2 by 5. Okay, 2 by 5, this one. But if you swap the order, okay, B times A, okay, B times A, B is 3 by 5, A is 2 by 3. But the 5 is not same with the 2 here. So that means BA is undefined. Okay, undefined. I give you one example. Okay, the matrix in front, okay, the first matrix, you list down the order. Okay, the order is 1 by 3. Okay, 1 by 3. And the second matrix has an order of 3 by 2. Okay, I didn't show my pointer. Come again. The first matrix, you have an order of 1 by 3. This one, 1 by 3. And the second matrix has an order of 3 by 2. This one, 3 by 2. So the nearer, okay, two nearer values, they must be the same. Okay, so the output has an order of 1 by 2. Okay, this is the output, 1 by 2. Okay, so how to get this? Okay, always remember when you want to do the matrix multiplication, always take the row from the first matrix and take the column from the second matrix. Okay, so row, column, you get the first one. Row, column, you get the second one. Okay, so this one, this row multiplied to this column, it means the first multiplied to the first plus the second multiplied to the second plus the last one multiplied to the last. Okay, this is called the row multiplied to the column. Okay, so then you get 17. Okay, so 1 times 0 plus 3 times -1 plus 2 times 2, you get 1. Okay, this is matrix multiplication. Okay, if you look at 3 by 3 matrices, okay, 3 by 3. So this row, you need to multiply to these 3 columns in order for you to get this 1, 2, 3 outputs, right? So second row, multiply to these 3 columns, you get these 3. Okay, and the last one, multiply to the 3 columns, you get the last 3 values. Okay. Okay, now let's say, okay, if you look at this one, this row, this is from the second row. This column from the last column. Okay, second row, third column. Okay, when you multiply these two, you will get the output at the location of second row, third column. It match. Okay, because this is from second column. This is from second row. Second row and third column. That's why the output is from second column, second row, and third column. It coincides. Okay. Okay. So remember, when you multiply two matrices, row first, row, then column. Okay, now we look at some properties of matrix multiplication. Okay, now let's say A has an order of n by n, and let's say B and C have orders for which the indicated sum and products are defined. Okay, this matrix multiplication is satisfying the associative law and also the distributive law. Just now, the matrix addition. Matrix addition is satisfying three laws. Commutative, associative, distributive. But this matrix multiplication is satisfying only the two, associative and distributive law. Okay. The one commutative law, what is the commutative law? When you swap the order and it's still valid, that is commutative. But this matrix multiplication A times B, is it equals to B times A? No, the answer is no. Matrix A times matrix B is not equals to matrix B times matrix A. If you don't believe, you can try it. That's why it doesn't satisfy the commutative law. Okay. Okay, this one, associative law, that means no matter you solve the last two or the first two first, you will still get the same answer. That is associative law. Okay, distributive law, okay, this one, A times B plus A times C. No matter it comes from the left or from the right, AB plus AC, you will still get the same answer. Okay, that is distributive law. Okay, so for any scalar R, okay, R is a scalar. This one is A times B. So this scalar will only be multiplied to one of them, either A like this or either B like this. Okay, because A times B, this is not A plus B. If A plus B, R must be multiplied to both. But this is multiplication. Okay, multiplication, so R will be multiplied to only one of them. Okay, either A or either B. Okay, identity. Okay, identity matrix, no matter you multiply to any of the matrix, you will get the matrix, original matrix back. Okay, so no matter I first or I later, the identity matrix, you will get the same A. Okay, this is identity matrix. Okay, this one is a bit special. Transpose of a product. Okay, transpose of a product. ABC transpose. It is equals to, you have to start from the last one. C transpose, B transpose, A transpose. Okay, this is transpose of matrix. So if you have A, B, C, D transpose, it will be D transpose, C transpose, B transpose, A transpose. Okay, you have to follow the sequence, but backwards sequence. Okay, power of a matrix. Okay, A power to the K. So let's say A power of 3, that means A times A times A. Okay, or 3 times. That is power of a matrix. Okay, there are some warnings here. Okay, some warnings. A times B is not equals to B times A. Okay, remember this. And the cancellation law, okay, it does not hold for matrix multiplication. Okay, for example, if you have AB equals to AC, we can't cancel out A by using cancellation law. Okay, we can't cancel out the A using the cancellation law and conclude that B equals to C. No. Okay, no, we can't do that. Okay, because the cancellation laws, it does not hold for matrix multiplication. Okay, even though AB equals to AC, but B is not equals to C in general. This is a fact. Okay, this is a fact. Okay, now another situation, let's say A matrix A times matrix B equals to 0 matrix. Okay, see, this 0 is in bold. In bold, the power here, right? Okay, in bold. So this is a 0 matrix. When you see just a 0, that is a constant 0. But when you see a 0 in bold, that is a 0 matrix. Okay, that's means all the entries are 0. So when A times B equals to 0 matrix, we cannot conclude that either A is 0 matrix or B is 0 matrix. No, it can be A and B are both non-zero matrices, but after they multiply to each other, you get 0 matrix. Okay, it is possible. Okay, it is possible. So we cannot conclude A is 0, then that's why AB equals to 0, or B is 0, that's why AB equals 0. No, we can't assume like that. Okay. Okay, so this is some properties of the matrix multiplication. The next one, primus. For this question, I will suggest or recommend you to solve the BC first before you multiply to the 3. Okay, if you multiply the 3 into the B first, the entries of B will be larger, the balance will be larger. Okay, it will be harder for you to do the multiplication later. The simplest way is to compute the BC first before you multiply the 3 into the product of the entries. Solve the AB first, compute the AB, then only find for the transpose of the product. Okay, so for question number one, after you multiply 3 into this, you will get this one. Proceed to number two. B transpose plus 2C. So this means Number two, one is sum of two matrices. We get this. Okay, for number three, verify associative law. Okay, what is the associative law? Associative law, we need three matrices. No matter we solve the AB first or BC first, then we go find to another matrix, we get the same answer. Okay. I write it here for number three. Okay, for number three, associative law is actually A, B, C. Okay, A, B first. A, B, C equals to A, B, C. Associative law. Okay, so you need to compute for this. Okay, then you compute for this. And finally, you see that these two matrices, okay, these two matrices are the same. So at the last, okay, you give the sentence A, B, C equals to A, B, C, and then verify. Okay, but you need to carry out this one. Okay, but this one, A, B, you have already got your A, B. Your A, B is here. Okay, you don't have to compute one more time. Your AB is here. Your BC already computed from question number one. You just take the BC from there. Okay. Then you compute. Okay. Compute them separately. Okay. You compute this one first. Get a matrix. Give this one, get one matrix, then at the end, you see that actually they are equal to each other, they are the same. But then we have already defined that has shape before. A from question number 2, BC you take from question number 1. Why we found that AB times C equals to A times BC. That means you have very high associated form. Okay, any questions? Anyone haven't signed for your attendance? Okay. I would take attendance for every single class, and students attend at least 80% of classes, right? I think you know this. In order for you to proceed to your final exam, twice you require so if it is less than 80% in attendance. So for my class, actually I'm quite flexible. If you absent because of certain reasons, really have let me know. Okay. And I will allow you to backdate your attendance by watching back the recorded video and work out the exercises that students did in the class. Okay, and then send to me. Okay, send to me in WhatsApp. I think all of you know you have my WhatsApp. Right? Okay, just send to me, then I will backdate your attendance. Okay, principle. Okay. But still, I hope my students can attend 100% of attendance. Okay. Okay, and for those who have joined the WhatsApp group, if you haven't sent your full name, please do so because I will send all the contacts. Okay, please send your full name in the WhatsApp group. Okay, and okay, today we will end here. So I'll see you on Thursday. 11. What time is our class on Thursday? 11. 11. Okay. So I will see you this Thursday.